Okay, so I redid standards 5.2 and 6.1. So for standard 5.2, it was the Fourier series and finding the coefficients. So what I did was I made up this wave and called this a period. It goes from -1 to 1, so the period is just 2. And in between the f of t is going to just be -t, a straight line through the origin. So to find an for this equation right here, to solve for ft and make this wave. So an is this equation. I plugged my f of t in and my bounds, and I get that an is equal to 0. And I did the same for bn with this equation, and I got this mess for bn. And b naught is always 0, and then a naught is this equation here, and that comes out to be 0. So our final equation for f of t is the sum of bn times sine n omega t. And what I did was I plotted that in Mathematica, and this is at n is equal to 1. So you see it's just a regular sine and cosine wave, but as you increase n and keep summing up these terms, it looks a lot more like the wave that we're looking for. Mathematica will catch up with me, hopefully. It's almost there, I promise. There it is. It looks a lot more like what I started with, and I'll just keep looking like that as I increase n, and Mathematica decides to work for me. There you go. So then for standard 6.1, I have the geodesic, the shortest distance, and what I did was I found it on a sphere instead of a cylinder, and I found it in terms of theta of phi. So I started out with an infinitesimal piece of a line. ds is equal to the square root of dx squared plus dy squared plus dz squared. And so x, y, and z in polar coordinates is this right here. So then dx would be taking the derivative of this first with respect to phi and then with respect to theta. So the product rule, sort of. And then dy and dz just do the same thing, except dz is a lot easier. And then so I plugged all of this into this ds equation, and I simplified, and I simplified, and I simplified. I eventually got down to ds is equal to the square root of r times d phi. I pulled out a d phi at some point because that's what I'm going to have to. I'm finding theta with respect to phi, so I'll integrate over phi. And so I ended up with sine squared theta plus cosine squared theta times theta prime plus sine of 2 phi, sine of 2 theta, theta prime. So this is theta prime squared, this is theta prime. And then I integrate both sides. This is all with respect to d phi. And then that is in the form of any function that I can use the Euler-Lagrange equation for. So this is f with respect to theta, phi, and theta prime. So to use the Euler-Lagrange, I found df d theta is this, df d theta prime, and then d phi of df d theta prime is this, and then I set them equal to each. I set this equal to this, because that's what the Euler-Lagrange equation is, and then you get this mess of a differential equation, and so I let Mathematica handle that for me, and I solved it here in this line, and then I plotted it. For some reason it has these two solutions. I'm not entirely sure why, but this one, you can see that I found from from 0 to 20. This one only went to 0 to 2. So this is the one I'm paying attention to. And so that's this purple line, which is a straight line, which is what we expect because the shortest distance between 2 points is a straight line. Yay!